R. And on Tuesday's class, we did some pretty fun stuff. Did you like doing that autoconvective lapse rate derivation?
Yes.
I mean, that was, we went off the cuff. I had never done this. I had never actually thought about doing it. And then we did it, and it was a lot of fun. So we did the derivation of why the autoconvective lapse rate is 34 degrees Celsius per kilometer, which is just really interesting, right? It's it's a cool thing. And we ran into a little problem, went online, found the solution. I'm like, oh, it's the hydrostatic. Then we can go ahead and do that. So just so interesting. We did some problem solving. We're done with that unit. So now we're going into the dynamics unit.
Yay.
Okay, so, you know, I'm excited about this. This is like a totally different feel, look and feel for this, which is fine, but it'll be different for you guys. And I think you're gonna like it. So I don't have Epic Pen on this computer because I don't have it for this computer. So I'm gonna be using a Word document to do my stuff. And whoops.
Epic Word document.
Epic Word document.
Oh.
And what I can do on this, because I was playing with it yesterday, is where I go to pens, and I got my pen. So here we go. So we're going to be, the only thing is I can't draw arrows really easily on this. So I'm just going to draw an arrow by hand, and I think that's fine. So we have a vector in two-dimensional space, right? And you understand that if you think about a two-dimensional graph, this is going to be X, this is going to be Y. I mean, that's the way the axes are typically labeled. Now, we know that in an axis like this, you know, we think of the arrow starting at the origin, and we call this the x-axis. We know the x-axis as really the zonal axis, and then the y-axis is the meridianal. So again, I'm going to the math ideas of x and y, but I'm going to be changing that.
With the abscissas?
The abscissa and the ordinate. Okay, which would be fine, but we do use x and y. I mean, that's just what's commonly used. For new kids, though, I think that's tough, but we're going to go a little bit beyond that. Now, do you understand that there is a component of this arrow that would go this way, right? And there's a component of the arrow that would go this way, okay? So let's say that this point is at 5, so x equals 5, and y equals 2, okay? How do I represent this vector? Well, one of the ways that you would represent a vector is you would go 5, 2. That's actually a point, but we're kind of getting the idea that there's a vector in here. So that's the point. That's the tip of the vector. What I'm going to do is I'm going to define vectors here, and I'm going to call this I hat and j hat. Okay, I hat is a unit vector. So, Mike, when I say unit vector, what do I mean by that? What do I mean by the term unit vector?
1.
It means the length of the vector is 1, right? That's what I mean by that. The length of the vector is 1. Hold on a second, I'm going to change something here. Do me a favor, if Jacob comes into class, let me know. I don't have my second monitor, so I can put your faces here. James, I know that you're here, but I won't see if Jacob comes in. So if he does, let me know, please. At this point, a unit means the value is 1. So I hat is a unit vector in X direction. What is J then?
Your vector
Y.
in the Y
In the
direction
Y direction. And then what would the vertical be?
is,
K.
In the K. And what I would use K hat. So that's the way you'd say this. J hat, I hat, K hat. And that means it's unit vector, just like unit kilograms, it's a value of 1. So the better way to describe this vector, and I'm going to put vector as this notation. That's the way that you are going to define a vector. And we'll talk about a couple things. The book, sometimes what they will do is they'll make it bold. So in a textbook, a lot of times vectors are bolded. Scalars are, just normal typeset. So here we have the vector v, in this case, is going to be 5 I hat plus 2 j hat. And that is the way you would represent this vector. Sometimes the vector may be represented, v is 5, 2, and it means the same thing. But this is the way that we're going to do this in this class. 5i plus 2j plus whatever k. I'm going to stick with 2 dimensions for a little bit. Now, do you agree that this vector and these green and red arrows are actually making a right triangle?
Mm-hmm.
Okay, and this length is 5, this length is 2. What is the length of the vector? What is the magnitude of the vector?
Square root of
29. Square root of 29.
Square root of 29, right? So, and I'm not going to worry about simplifying that at this point, but it's Pythagorean's theorem, right? A squared plus b squared equals c squared. So when I represent magnitude, I could say this. I could say v is equal to the square root of 29. But another common way that you'll see it is this. And that format means magnitude. So it's the absolute value signs around the vector is telling you the magnitude. And the magnitude of a vector is its length. So if I'm dealing with speed, I'm dealing with, the length of a velocity vector is the speed. Okay, that's what I've got. Does that make sense? Because I don't know if you necessarily know this or if this is new to you or you have forgotten it. So if you don't understand something, you need to say something, but at this point, I'm okay. All right. Now, do you also agree that there would be an angle here? How do I determine that angle? Well, I'm going to call that angle theta. And the easiest way to do that is the tangent of theta. If you remember SOHCAHTOA, the tangent of the angle is the opposite over the adjacent. In this case, 2/5 or 0.4. So take out your calculator or on your phone, because again, I need you to practice this to make sure that you're using your tools correctly. If the tangent of theta is 0.4, take the inverse tangent. Inverse tangent should look like this, tan to the minus. Oh. So inverse tangent of 0.4.
(21.8 degrees).
Does everybody have 21.8 degrees?
Yep.
Good. James, Jim, are you good with that?
Yep.
Yeah.
Mike, you got that on your calculator or your phone?
Nope.
What did you get?
.380. Hey, let me just,
Okay, so you are in radians. You need
Radians.
to put it into degrees
all right.
because degrees are going to be the common way that we do stuff.
Yeah, you're right. Shoot, I don't know how to do that. Yeah, there we go. Wait.
All right, you got 21.8 degrees. So we know that's 21.8 degrees. Okay, now we're going to deal with the meteorology of this stuff. Okay, so the meteorology of this stuff says that we have north, west, south, and east. So we know that this angle here is 21.8. What do we need to measure wind direction from? Do you agree that wind direction is always measured from the north? So you could say that the speed of the winds is the square root of 29. Somebody tell me what the square root of 29 is, would you?
5.38, 5.39.
5.39. Okay. You know what? Let's just make it easy. Let's just go 5.4. How about? Okay. And what direction would the wind? So we'd say
248.
the velocity of the wind is 5.4 knot or meters per second. I'm going to use standard at what? 69.2.
Huh?
What are you looking at?
Remember, we know that this angle is 21.8.
Mhm.
So we want the complementary angle. 21.8 plus 69, 68.
No, 270 minus 21, right?
No.
90?
This is 0 or 360.
Oh,
Oh,
This is 90.
right.
So we would say the winds are 5.4 meters per second at 68.2 degrees.
Yep.
Right, because an east wind is a 90 degree.
Okay, question, but the wind is blowing to that direction, not from the direction.
Southwest.
If you understand what I'm saying.
Jim, I understand what you're saying. What
Okay.
you're not understanding is you have to think incorrectly like I just did.
Okay.
Okay? Because if you did it right, you would have said, okay, I'm embarrassed. I'm stupid. I'm not really stupid. I'm okay with myself. But I'm embarrassed because I am totally not. Yes, that angle is from the north. You're right. But the winds are named whence they came. So the winds are coming from this direction. So it would be 270 minus 21.8, which
Which is
makes it
248.2.
248.2 degrees. So Jim should be teaching the class, and I should be going, oh, dude, I need a better grade at my next test.
If it makes you feel any better, I'm still trying to figure out how to get this fucking calculator into degree mode because I'm so stupid.
Do you have a button that says load?
I found it. It's because for Christmas last year, I'm a nerd and I asked for the most expensive calculator you can get, which is the TI-CX2, and I'm really technology challenged, and so I'm so used to the TI-84 that I'm trying to teach myself all this stuff now.
Oh, I know how that works, and trust me, I was in a car the other day. It was a GN, a German car, and the stick shift is like push button, but you have to pull it back to go into reverse, but you hit a button to make it park, and then you have to push the side button and push it forward to go to. I'm like, the hell is this? Why can't I just do a stick shift? Like
why
I
do
used
you
to
gotta
do, right?
overcomplicate everything? I'm like, so like this is supposed to be the best calculator, like, and I'm just like, do the things that I want you to do.
See it like
you young
About an
inspired.
HP.
It's, yeah,
you
kinda-
young people know this, but there used to be a time where you'd buy a car and they'd go, here's the keys, and you drive your car.
Yeah.
And now you buy a car, they go, okay, come, we'll meet you here. We have a guy who's going to give you an hour tutorial on how to use your car.
Oh no. See, I
Oh
got the,
boy.
That's
I
an
get the
Inspire, right?
cars. Yeah, it's the Inspire.
Okay, I'll send you instructions then in the chat.
Okay, thank you.
Oh,
Mhm.
you're a good guy, Nick. Okay, so does everybody understand how we got the wind direction? But
Yeah, I get the number now.
what if I said this is a vector of the wind? Do you agree that it would be 5I plus 2J? But now, in meteorology, what is this wind? Are these positive or are they negative?
The individual terms?
Yep.
Oh,
The 2 is negative because that's no. Positive. South.
A wind from the west is positive or negative?
Negative.
Negative.
Wind from the south is positive.
No, wait a minute.
Okay, so now you got to get into your book and go back to the first.
It's going toward the east. It's the direction of the vector.
Right. So now we go over here to, in your book, to the very beginning of the book. And we go U is 1.2 is dx dt. So the change in x positive is to the east, positive is dy dt, which is
To the north.
So
Okay.
in both of these, this would be a positive.
Positive number.
Yeah, you don't have to put positive in there. But what if the wind had been the other way? What if the wind had been something like this? Then the vector would
Would be
be
negative.
negative 5I, or minus 2J.
Okay.
As a vector is concerned. So the biggest problem that we're going to have in these scenarios is to figure out where the vector is in this coordinate system. So this side, and maybe this is a better way to do this, this side is plus plus. This side would be negative negative. This would be plus negative, and this would be negative plus. Positive U, positive V, positive U, negative V, negative both, and this is a negative U, positive V. Okay? Is everybody good with that?
so far, so good. This is something I remember doing in a previous class several years ago. So,
Well, I hope we get the idea of this. Now, if I took this vector and I said I wanted to add it to this vector. So let's say that I took the vector, I'd say A equals 5I plus 2J vector, and I usually put them in parentheses, plus, and then let's say that this one is, I don't know, negative 1I hat plus 3J. So to add vectors, I take one vector's tail, hook it to the head of another, and then I connect the loose ends. Right? That's how I would do it. So all I do in this scenario to add vectors, it's if this is vector, so the added vector is going to be this vector, black plus red, and I add 5 plus -1 is going to be 4i plus or minus 1. Sorry, 2 plus 3 is 5j. I just add each term, i's and j's. And the same thing would be done as far as vectors are concerned in three-dimensional space. So a lot of times it might be better if I did this. 5, 2 plus -1, 3 is equal to 4, 5. So the blue vector goes over 5 or over 4 and up 5. So vector arithmetic is pretty simple. When I subtract a vector, do you understand how easy that is? I just subtract. I add the negative. Just so you know, I'm gonna draw this vector again here. So I'm taking this vector minus this. So minus this is plus the negative. And then the resultant vector would be something along these lines. If I subtracted those two, what would it be? 5, 2 plus -1, 3. But I'm subtracting, so it's going to be that. And that's going to be 6 and -1. And it makes sense because the red arrow is going to go to the right positive by more, and it's going to go negative.
Okay. That would be for A minus B, whereas if it was B minus
A minus B, right, yeah.
where if it's B minus A, the arrowhead would be on the other end.
Exactly. So you just have to think that adding vectors is easy. Subtracting vectors is adding the negative of the other vector. So you could simplify that by, something like this. You could say A vector plus B vector equals some other vector. That's easy to do. A minus B is really A
plus B.
the negative of B.
Right. Yeah.
And that just reverses it. That just changes the positive to
sense.
negative. That's it. Now, the question is, what if I decided I want to multiply vectors? So let's do this. Let's take an example. I'll stay with the same one. Vector A is 5i plus 2j. B was, what did I have the first time?
2j.
Was
Or
it
no.
1?
-1, 3.
1i minus 3. That's fine, whatever. Right? There's my vectors. And now I want to multiply them.
Someone drilling in your background?
I'm getting my room destroyed, so they're knocking out a wall.
Okay.
They're 2 floors up.
No, I just couldn't figure out what that background like high-pitched squeal was, and I thought it was I was going crazy, but now
I don't hear any of that.
I mean, could be both, right?
It's like somebody's firing something or something. I can hear it.
Like a teapot going off almost.
Yeah.
Oh, really?
I don't hear it. I don't hear it.
that. That's not here.
Very,
They're
very-
pounding on things. Go. Anyway, the thing that I'm going to start by saying here is that this there's two things that you need to know about. There's two ways to multiply vectors. Do you remember if I add two things, a plus sign is what? Like 4 plus was, the answer is called the what?
Sum.
The sum.
Um,
Subtraction is what?
Difference.
Difference. Okay, and what's multiplication?
Product.
Product.
Product, if you remember that. By the way, do you know what division is?
Quotient.
Quotient.
How do you guys know that? Are you just that
Product.
smart?
We went to elementary school.
Yeah,
no.
exactly.
No. The way I think of it is product rule from calculus and quotient rule.
Oh, there you go. Calc helps you learn this stuff. That's true.
It's
So there's two ways to do this. The first way is called a dot product. The second one is called the cross product. So what I put in here, so look at this screen here, guys. With the dot means something. You can't just do whatever you want. If I do a cross product, then I'm going to get A vector cross B. And these are not only are they two different operations, but they do totally different things. So the first one we are going to do is the dot product. So dot product is if I have a vector x, y, j, I'm sorry. X, Y, Z dotted with A, B, C, it's going to be X times A plus Y times B plus Z times C. I just take each of the I, J, K components, multiply them, and then I add all of them together. So in this vector, what is A dot B? It's going to be 5 times 1 plus 2 times negative 3. That's how you do it. Doing is easy, right? But what does that mean?
You get two vectors and you get a scalar product.
You get a scalar.
So first of all, I get a scalar. So good that you recognize that. I get a scalar when I do this. Okay? But there's something else that's really cool about this. It is projection of one vector on another. So let's see if I can draw this. This is where I wish I had my Epic pen drawing straight lines. I know I can do that here someplace, but so the first arrow is 5 plus 2, so it's this. And the other one is 1 plus negative 3. Here's something that's really interesting. Okay.
Okay.
So calculate theta. It'll take a minute or two, but you have the ability to do this.
Bless you.
Thank you. Thank you.
What do you guys get? Do you have an answer yet?
92.95 degrees.
Seems about right based on the drawing, doesn't it?
Mm-hmm.
How about you, Mike and James and Nick and Allison? Do you guys have that answer? Because I need to know if you get the answer.
Don't get that answer. Wait,
Okay.
what were you specifically asking for though? Were you asking just for the angle for the one in the fourth quadrant or?
No, no. I'm looking for the angle between those two vectors. So you have to figure out the magnitude of A, right? What is the magnitude of A?
Square root of 29.
Right. Which we already said, right? And what's the magnitude of B?
Oh,
1
that I,
squared is the magnitude, is square root of 10, right?
yeah, hold on. I got a slight error.
3.16.
93.3.
But what's A cross B? We said -1.
No, A dot B.
I'm A dot B, right? So we said that's -1. So -1 equals the square root of 29 times square root of 10. So you solve, and what do you get? Cosine
Oh, I did it a completely different way.
equals what? -1 over square root of 29 times the square root of 10, which is, it's a pretty small number. It's going to be close to 0, or which mean, I mean, the cosine of what angle is 0? And the answer is 90. So it's going to be close to 90 degrees. But it's negative. So you take whatever this is, you take the inverse cosine. So what is -1 over the number equal to?
93.4. I got it a completely different way, but
Okay,
I
hold
got the same answer.
Let's before we do that, let's talk about what's -1 over square root of 29 square root of 10.
It is 290. Oh, it's sorry, my calculator just put it as -290 over 290. So if anybody else has the actual number.
What's this calculation?
-5.87.
What is it?
-5.87.
No. Just give me the number. -1 over square root of 29 times the square root of -10.
Negative 0.0587.
Oh, okay. Yeah.
Say again, Allison, negative.
0.0587.
Okay. And then I take the inverse cosine. So the inverse cosine, just like anything else, you get me the theta, is the inverse cosine of that number.
Mm-hmm.
If you're in radians, that should get you theta equals
93.4. Do you want to hear how I originally did it?
yes.
The way I originally did it is because we found already the angle for the first one, which is the 21.8.
Okay, and then you figured out the angle for the second one and added. Okay, so
Okay.
good. You figured out this angle, and then you figured out this angle, and then you added the two,
Yeah.
which is fine, right? This is the way that you make life a whole lot easier.
Yeah.
Okay, so now that we have, does anybody have a question on this?
So
'Cause
far, so good.
Okay, so then let's do this. Let me go back to an example here. Imagine that I have a vector and that's the vector. And that's theta. That vector is going to be what generalized?
I plus j, if that's what you're getting at.
How much is I? And how much is j? How much I?
Oh, I see what you're getting at.
Oh, I see what you're doing. You're doing, yeah, the trick.
Right. Okay. I see.
So I want you to think of this as being a light source. Okay, and the light is shining on this vector. And when the light shines on that vector is going to cast a shadow that is this long. So the light shining down, it's casting a shadow that's that long. Do you agree that if theta were 0, the length of the vector and this red vector would be the same? Cosine of 0 degrees is 1. It's the length of the vector. If I put the sun over here and it casts a light that way, then this vector length would be what? V
The second term.
times sine of the angle. Because if theta was 0, there'd be no green arrow.
So the green and the red arrow are the projections on the respective axes.
So yeah, so in simplification terms, this is how you would have a vector. I'm just rewriting it. And the magnitude of those vectors. So let's try one. What's the vector? Actually, you know what I think I'll do for you? Because I'll be nice. I'll be nice to you, first of all. No, I'm not going to be nice to you. Yes, I am.
Good Paul, bad Paul. I guess it's that kind of day.
There we go.
Well,
I'll be nice to you that way. I almost did the same thing I did earlier. Tell me what the vector is.
so if we're talking about from where, if we're listing at where winds come from, we are working in the first quadrant then, right?
Yeah, well, what you're going to need to do is you're going to have to figure out if that like this arrow is similar to what 238. So then the question is, this is the angle, and we know that that full angle is 238 degrees, right?
Mm-hmm.
But I want to get to this angle.
Yeah.
So what I would say is, okay, then if that's the case, then what's this angle? And what's this angle? Can you figure that out? This angle, actually, you don't need this one, do you? You need this angle. So what is this angle? It's 270 minus 238, which would be
32.
2, which means this
That's-
theta
is 32.
32. And I know they're 23, so what's the vector then?
At 31.7?
It's 23
Oh,
times
cosine of
Cosine.
32,
of 32 plus
23 sine of 32.
times the sine of 32. And when you do that, what do you get, Jim?
31.7?
No.
No.
Okay. What's 23 times the cosine of
Oh.
32?
23 times cosine of 32 is 19.505
19.505
meters per second.
meters per second.
I had
Hat plus
Oh, oop, no, wait.
12.188 meters per second. J hat.
31.7.
right. It can't be more than, because your cosine's always less than 1.
Mm-hmm.
1 or less or smaller. So do you understand that doing the actual calculation is easy? What's the hardest part is figuring out what angle this vector is.
Yeah.
So this is the positive side, but winds are all named differently. So there's a conversion that you need to do in your brain. So what is necessary step of any problem that you're going to solve?
Figure out what that angle is going to
Drawing,
be.
right?
A complementary angle.
Right, you got to draw the picture. And just remember that we've got congruent angles across parallel lines. Okay? So hopefully that all makes sense.
Mm-hmm.
Yep. Just something I think I need to practice on.
Okay. Let's do this. Let me go to how a cross product works. Best way to do that is to show you a three-dimensional vector, because I don't care about two-dimensional cross products. So I'm going to show you a three-dimensional vector. So I'm going to say that A is AI hat plus BJ hat plus CK hat. And I'm going to go B is DI hat plus EJ hat plus FK hat. So are you okay with that?
Yep.
Okay. Over here, that cross product, therefore, is going to be a matrix. and I'm taking, do you know what the app, so do you know what a matrix is? It's just a way of describing stuff. You know what this is called when you put the absolute values around a matrix? I'm calculating the determinant.
Permanent, yeah.
I think that's how you spell it, right?
I think ANTE.
I don't think I've ever written the word determinant. What is the answer?
What? The spelling?
Yeah.
Determinant. I think you got it right.
Determinant.
And yeah, you've got it right.
Okay.
I got my copy of Thomas with me.
Okay. That's fine. So, how many of you have never done determinants of matrices?
Think so. Maybe.
You have done them, Mike?
Maybe. I can't remember.
Okay. Nick, you've done them?
Yeah.
And how about you, James? James,
Yes.
have you done determinants?
I don't think so.
Okay, so what I'm going to do is a determinant looks like this. So I need to show you this process. I'm going to take this guy first. So the first thing it is something times I hat. And when I'm looking at the value of this guy, I'm going to block out this and this. Okay? And I'm going to take this B times F minus C times E.
So this is when solving for I, correct?
Yep. So in doing the cross product, which is a multiplication of vectors, I write IJK in the top line, in the top row. I go ABC in the second one and DEF in the next one. So that's what the vectors are. And it's going to be this minus that.
All right, that's pretty simple.
Okay. Now, if I'm going to do J, oops, what happened to that? I erased B. If I'm going to do J, I'm going to block out these lines. And I'm going to go A times F minus D times C. And that's J hat. And then the K hat, I keep erasing things.
So you cross out the lines that are next to it, and then you just multiply.
And I go this, whatever's left. And I'm only going to be doing this 3 by 3. So the last one will be A times E minus B times D K hat. There's only one little stupid trick, and I don't, like, if you get into math, you will learn this. When I look at a matrix like this, I don't even know why they do this. They just do this. They look at a matrix as being this way. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So that means the I term is plus. But what's the J term?
Minus.
Minus. And then the K term is back to plus. So what that tells me is this, guys. What that tells me is this. I could have thought of the J section. Watch this, guys. Instead of A times F minus C times D, I could have gone backwards. C times D minus AF in the J hat. Because if that's a minus sign in here, then that becomes minus AF, and that becomes a plus CD, see? So I sometimes go this minus that, or I go the other way for the J term. Either way that you do it is fine, as long as you remember that's what it is.
All right.
You guys want to try one for an example?
I think so.
Okay, well, I'm going to do this then, simple. Do I need to save this for you?
Got it all written down.
Got it all written down. Okay, then I'm going to get rid of it. Then I'm just going to I'll make it simple.
Both unit factors?
Make it simple. And I want you to tell me what's A dot B and what is A cross B.
Are we doing dot and cross product?
Yep.
Okay.
That's easy.
A lot of minus twos.
Yeah.
Paul, you're off on the I.
-6.
Yep.
Because the -2 times the -2 becomes a positive, but you still have to subtract the -4.
Right. So -6 minus -4 minus 4 is
Oh.
-10.
That's what I concur with Paul.
No, you're right. I wrote a sign wrong.
Okay. I mean, that's right. Signs in mathematics are your biggest areas for error. And they're stupid errors. And they're not. What bothers me about signs is it doesn't tell you that you're smart or dumb, that you understand a concept. You're just making a mistake. You
Mhm.
make mistakes. So that's it right there, right?
Yeah. And to be clear, you can, like I think you said it, but like once you multiply in one direction, you can just swap it out. You can, yeah,
Yeah. What I did here, Jim or James, is I went negative, right? 4 times -2. I'm sorry, for the I hat, I'm like 3 times -2 is -6 minus 4. -10.
gotcha. All right.
For
Yep.
the J, right, for the J hat, so again, I'm going here, I'm going -8 minus 4 is -12, but it's minus that, so it's plus. But I just do backwards. I practice doing this. I'm like -2 minus 4, 8 minus a -8, positive 12. Either way, it comes out to be the same.
All right. Yeah, that's pretty simple. Just need to get that practice
So
down on
on
that.
that last note, so remember you said the dot product was a scalar. The cross product is a vector. And this is where things get really fun. Because here's where life becomes amazingly cool. I want to do something. Here. And I want to say, well, what if I took a vector? 4i plus 1j plus 2k. And I multiply that vector by a scalar, 2. This is a parentheses. So what does that become?
Other vector.
Right? A scalar times a vector is a scalar. So that's easy, right? Tell me that's easy. We're almost to the exciting point. Can I move on with that? Everybody got that done?
Yep.
This is fun. Here's a cool thing. Try this. What's I hat cross J hat? Oops. Oops. What does that equal?
Paul back.
Oh, there we go.
All right.
Okay, so they didn't get you.
We're
Okay.
doing construction, so if the power gets stopped for a second, that may be a problem, but I was
We
able to
thought
do.
we
I was
thought
able
they
to do
took
something
down the
different.
wall that had your internet in it.
That's okay. I've got alternate methods. I am still recording.
Yes.
Okay. Okay, there we go. What's the answer to this?
Okay.
1.
No, not 1.
1K.
K hat, right?
Right.
Okay, so watch this, guys. You see this diagram? This is the 3 vectors. This is how you draw a 3-dimensional coordinate system. So if I is, like we know, this is east, this is north, and that's up. Right? So I want you to take a look at that picture and take a look at, put your right hand, put your right fingers in the direction of I. Okay? So you're going to, whatever you envision I to be, then curl your fingers to J hat. And then put your thumb up.
Right hand rule.
That's the right hand rule. And that's because a cross product is known as the curl. You are curling your fingers. So without doing the matrix, what is J cross K? So put your fingers in J and then cross up. Which way would you point with your thumb? Which way are you pointing with your fingers? What's the answer?
J.
J cross K
J cross I is this way.
would be what? James?
Give
Uh, I'm trying to get my hand to work correctly here to actually make
Right.
this motion, but for some reason it's like,
K.
You got it. You have to look at that little diagram and just think about your right hand going in whatever direction you need to picture that. Isn't J cross K pointing in the I direction? What's I cross K?
J direction.
No.
Oh, there can only I cross K.
Here. Couldn't you do it like this?
I.
Negative J.
I cross J or I cross K would be negative J. Do you guys see that? Allison, are you there?
Yeah, I see that.
Okay. Yeah, hold on, I need to do this.
I've always just preferred doing it the mathematical way.
I mean, if you did it in this matrix, in the determinant, you'd get the same answer. But the more important thing is for you to visualize what's going on, because that's what a cross product is. It's the right-hand rule of stuff.
Is the left hand rule ever used?
No, well, Southern Hemisphere.
Thank you.
do you live in?
So Okay? Does that make sense? So you could practice these things, but you got to see that. So the key to this is that the cross product is always a vector that is perpendicular to the other two vectors. Right? Do you know that to be a fact?
Yes.
Then this is stuff, right? This is, I mean, do you know that? Because I'm telling you right now, most important thing for you to know is that is always the case. The most important thing when you do a cross product, that resultant vector is always perpendicular to the other two vectors, which means what? It means if I take vector A cross vector B, which is going to be a vector C, then what's a, oops. What is A dot C going to be equal to?
The magnitude is A dot C. Okay.
But what do we say about these? The resultant vector is always what? Perpendicular. So what's cosine of the angle between the two?
0.
Cosine, well, the angle's 90, which means that this term goes to 0. So A dot C, which is also equal to B dot C, is always 0. Because the dot product is a projection of light onto the other vector. It's the magnitude of the vector, basically. So if you have two perpendicular vectors, will you project any light onto the other vector? The answer is no. So those facts on this page are like, they've got to be drilled into your mind, because when we start dealing with vectors, you're going to see how important this becomes. We're going to talk about geostrophic and divergence and all this other stuff that will be amazing to you if you remember these facts. I'm giving you a heads up to this. Okay, now let's do this. Do you agree that del is a vector?
Uh-oh.
Am I still there? Am I there? Hello?
We're losing you, Paul.
Do you hear
Yeah,
me?
you're here.
Yeah.
Yes.
A
That's
rubber
better.
band.
Bandwidth dropped out.
Okay, well, yeah, that's that. I'm using my cell phone as a hotspot, so I'll go back. I'll go back to my other one later. But I'm not going to do that right now. Del can be written as a vector. The question is, how do I multiply vectors? I can do two ways. If that's the case, and the velocity is actually ui plus vj hat plus wk hat, then what does that equal? Now watch this, guys. I'm multiplying this times that. When I multiply this operator, do you understand? I'm just going to go du dx. Because it's a dot product, is this going to be a scalar or a vector?
Oh, vector.
No, dot product,
Dot product is a scalar.
scalar. So they sometimes will call the dot product the scalar product.
Okay.
So it's going to be that plus dv dy plus dw dz.
So we drop the vector, I and j and k hat notation once you
Because
do the
that goes
actual.
away.
Right. Okay.
Okay, so this derivative here, Mike, how would you say this derivative in like English?
A change in the u direction over a change in x.
No.
A change in the
What
change
is
in u.
u?
over x.
What is u?
Shit. Is it the east-west direction?
Well, yes. So what do you call that?
Shit.
What's the word?
Magnitude?
Zonal.
Oh, yeah.
Right, zonal.
Oh,
So u is the what?
Zonal
That's
velocity.
the zonal wind. And that zonal wind changes as I travel.
Shit, what's x?
What's x?
Distance.
No.
change in location.
Okay, Shannon.
Yeah, but what is delta x is what? As I travel what? Right? That's a question. How
From
does
west
u
to-
change with respect to
From west to east.
So this is a change in the zonal wind as I travel east. And if it's positive, what does that mean?
You're moving
from the
eastward.
It's out of the west going to the east.
But what's different?
You're just moving westward if it's negative.
You guys are, this is why students don't do well in this. You're not thinking about what u is. Look, u is a vector.
Right.
There's the wind. It's a zonal wind. Or it's a speed. It's a wind. As I travel to the east, what is happening to the wind?
Accelerating?
Moving.
Isn't it getting faster? Isn't this diagram
Oh,
du dx? Positive du dx.
Mm-hmm.
What is that? What's it doing?
accelerating.
What's it doing? What's that called?
Advecting. Eastward.
No, it's not advecting.
Divergence. Oh my god.
Oh, it's divergence.
Isn't that diverging? Isn't that divergence?
Okay.
Yep.
So what's dv dy look like? That means I'm going this way, and as I go to the north,
It's
the winds are
diverging.
getting faster.
Right.
Negative.
So I'm going, so how does the meridional wind change as I travel north? That's what I'm saying about this. See, and this is what students, Allison, this is what your compatriots at Texas A&M probably have a hard time. They look at that, and what do they think this is? They think this is math. That is not math. This is meteorology. This is the southerly wind is changing as I move north. How does the southerly wind change as I move north? If you're not thinking that way, you're going to struggle with this. But that's what it means. What's this?
How the zonal wind,
No, this one?
not zonal,
Vertical.
vertical wind change with height
No, don't say it would change as you go
go in the
up.
Higher.
up.
As you go higher, the air is accelerating. Do you agree that all of those are divergence? So guess what this becomes, boys and girls? Del dot V is called divergence. After Calc 3, at COD at least, you have a 1 semester hour course called vector calculus.
It's after.
It's after the semester's over. And they say del dot V, and you deal with this, and they call this the divergence of a vector. Well, who knows divergence better than meteorologists? The answer is nobody. We know what that is. Okay, now, do you remember we said, well, what if I took this acting on a scalar, like temperature? What does that become? Hold on, let me. What does that become? You agree that is just this vector. Instead of multiplying it by a vector, I'm multiplying it by a scalar.
Scalar.
So it's just, I put t in there. I get dt dx I hat plus dt dy j hat plus dt dz k hat. Okay, well, how do you say this first term? How do you say that in English? Go ahead, Allison. You go first. You're muted. I don't hear you. You're not muted, but you weren't working. Anybody else? Does anybody else hear, or is it just me?
Oh, I don't hear her at all.
I don't hear her either.
No.
I don't think she's hearing us.
No, she hears us.
Wave your hand if you can hear us, Allison. Okay, she
Yep.
can hear us.
Okay. So, Nick, how do you say this first term in English?
The temperature gradient, the zonal temperature gradient.
It is, but how do you say this? Remember,
Yep.
that's the question. How does,
The temperature change from east to west.
well, no, be careful. As I move,
West to east.
West to east.
so you'd go,
West.
how does the temperature change
Yeah.
as I move east?
Mm-hmm.
So do you agree that if I have an isotherm here that's 70, and I have an isotherm here, let's say every 5, positive dTdx would be what? Would this be 75 or 65?
Would be 75.
It has to be 75, right? Because as I move east, positive X, temperature is positive increasing.
What could you say something about the isotherms as well, since the temperature is accelerating?
No, you wouldn't say
No.
that. You just
Okay.
say there,
Okay.
and Nick said it. This is called a gradient.
It's a gradient. Okay.
Mm-hmm.
So del operating on a scalar is called the gradient. So do you know what they call del dot a temperature? They call this the gradient operator. But here's the key thing. What is a gradient, really? And this is something that we've never talked about. What is a gradient?
It's a change in something over a given distance.
It's more than that. It's a what?
Constant change?
A gradient is a vector.
Oh,
That we've never said in any of my classes. We know what a gradient is. We know a strong temperature gradient, but a gradient is a vector. Which way does it point? Toward higher values.
toward higher what?
Higher values.
Higher values. It always points uphill. So hold on a second. So do you understand the del dot, the velocity is divergence? That del dot, a scalar, is a gradient. I want to show you something kind of cool here. Which way does the pressure gradient force point?
Higher to lower.
From high to low pressure. That's why whenever you see the pressure gradient force, you're going to see it as this. Like if I did this, dp dz, minus 1 over rho dp dz. Because which way in that example, the pressure gradient force is pointing up toward lower pressure. But what is the value of this guy here? What's the magnet, like the,
It's positive.
no.
What?
How does the pressure change as I go up? The answer,
Oh.
this is negative.
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 But a negative
Negative is a positive.
is a positive. So to this force that we said the pressure gradient points toward low pressure has to be negative that, because a true vector points toward a higher pressure gradient. So the pressure gradient force is the negative because dp dz is positive when it points to higher pressure. Are you guys understanding that?
Yeah.
Yeah.
Okay, here's something. Again, I think this is cool.
For me, because I've been doing this in class, but
Yep.
it's been kind of, now it's making more sense now.
So here's the thing, Allison, and this is why this is the problem in meteorology education. The calculus you do is pretty straightforward. And I've always been able to teach calculus to those with algebra backgrounds. The strength of the calculus is in the understanding of the concept. It's the language of it. The actual mathematics doing it, that's easy. I can do cross products. I can do dot products. That's easy to do. But understanding what I'm talking about is tough. So what is this now? This is a gradient.
Gradient.
And a gradient is a vector. And so if I take a vector times a vector, this is the velocity vector, dot a gradient vector, what do I get? I get a scalar. You know what you call velocity dotted with the gradient?
Advection.
That's advection. So if I have this as temperature advection, this is the equation that says temperature. I see this, I say temperature advection, because the velocity dotted with the gradient is always advection. Do you agree that I could also do this? And now I'm advecting pressure gradient. That's pressure advection. But the problem is, and so watch this, this is where power comes in. If this is geostrophic, which way does the pressure gradient force, well, which way does the wind flow?
Parallel.
That's the velocity. Which way is the pressure gradient force point? From high to low pressure.
Orthogonal.
Pressure gradient force, which we know is -1 over rho dp dx, or in this case, whatever, or dy, whatever it is. Don't worry about that. But do you understand that those are orthogonal? So what's the dot product of two vectors that are perpendicular?
Zero.
0. So do you understand that if the air is flowing parallel to pressure, I am not advecting mass. I'm not moving air. I'm not advecting the pressure change. I'm not changing the pressure, right? If I'm advecting temperature, do you agree the temperature is changing? If I'm advecting pressure, do you agree the pressure would change? But am I advecting pressure? No. Which means, will the pressure field ever change? No, which means the winds are what the winds are, which says that the geostrophic wind is non-divergent because I'm not changing anything. Okay, so watch this. What if instead of pressure, I said that was temperature?
There you would get advection.
With this velocity, if the wind is blowing parallel to the isotherms, am I advecting temperature? If I have no temperature advection, right, which is what's that, we say that's barotropic. But if the isotherms were dashed like this, do you agree that they're no longer parallel anymore? And I'm advecting. And what do we call it when isotherms intersect isobars?
Barometric. No, baroclinic, sorry.
Baroclinic. Okay, now, does that make sense? So I've defined gradient, I've defined advection, I've defined divergence. Do you agree that I could also?
1040, Paul.
I know. I'm going to do 2 more things because it's fun. I'm advecting divergence. That's mass advection. I'm advecting mass. I can advect things. So I can, as long as it's a vector, because velocity is a vector, I can do this.
So it's a vector times a vector times a vector.
Yep. Which makes this,
Scalar.
no, a vector.
No.
Because what's this? That's a scalar.
Oh,
Scalar times a whole vector
yes.
is a vector again.
Mind the parentheses.
Okay. Now, let's do one more thing. What if I did this? That's called the curl of the velocity vector, right? That's the mathematics term. But do you know what we call this in meteorology?
Vorticity.
Do, 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 do.
Del cross V. Is
Cross
vort-
vorticity.
And what vorticity is a what?
A gradient.
No,
No, it's scalar cross a scalar.
no. Vector cross
Or
a
a vector cross a vector, it's a vector.
Vorticity is a vector,
It's a vector.
which we've done, right? So we're saying my right thumb is the vector. Chuck Doswell, do you guys know who I mean by Chuck Doswell?
Yep.
That was his license plate.
Del XY.
Del cross V. Del cross V, because that's what's a tornado, vorticity. So here's your assignment for next Thursday. And I want you to do this, and I'll okay. Two things. First of all, whoops, I want you to write the vectors and draw a picture of three-dimensional vorticity. So I want you to do this using two vectors, A, B, C, D, E, F. No, I lied. Using, what would the vector that you'd use? UI plus VJ, right? Plus WK. So I want you to do that cross product and then draw a picture to show that using arrows. So that's first one. Okay? The second problem is this. I will want you to email me the answers to that. Don't do it on Blackboard. Just email, because I'm assigning you grades based on what I see.
And what was that that vector in the first problem again?
UI plus VJ plus WK.
UI.
You're doing the actual, you're showing me what the
Yeah.
three-dimensional vorticity vector looks like.
Okay, so just calculating that out. All right.
Yep. And then this one. This is just a velocity. This is just trying to figure out what the vector is to represent that.
Sorry, what was the first thing we had to do again? I was finding a piece of paper to write this down on. Tearing it out of my.
Do that using UVW, and then I want you to draw the arrows representing those derivatives. Because you have to visualize what three-dimensional vorticity looks like. But I want you to send me an email of this problem here.
This is for next Thursday?
Yeah. And then you should continue reading in the next chapter. But really what you should be focused on, because this is only going to take you half an hour and you have a week, you should be doing your final project.
Oh,
because there's a lot of work on that. So you have a week to get a good start on it. Okay, does everybody got that? So that's what you should be doing.
Mhm.
Okay.
Paul, as a sidebar, in Word, what do you use to write equations?
They have an equation editor in here.
So
So
that's what you use? Okay.
yeah, I would,
You don't?
it's not the greatest, but I can do it. And it's got
Okay.
everything I need.
Okay,
It's
that's
a
good
little bit
enough for me.
slow, but I like it.
Okay.
And it makes everything neat. Now, the other way you could do it,
I know you can put in LaTeX, but it's not the full LaTeX.
look at this, guys. Ink to Math. I
Oh.
can do,
Share it.
oh,
Is that the name of the package?
in Word, I have Ink to Math.
Oh, change handwritten ink to math in OneNote.
I'm
Okay.
not sure if that's really doing it.
Doesn't like
It doesn't like Dell operators.
maybe. Nope.
It does not. But equation editor does.
Okay.
hmm
All right.
Okay, guys, have a good week. I'll see you next Thursday. Okay, that gives you a week, so you should get a lot on your final project done.
Cool.
And I'll see you at noon, Paul.
I'll see you at noon. Do you want to just say now and do it right now? You got 10 minutes. You think it'll take more than 10 minutes?
Good question, Paul.
Yeah, I'll see you at noon, Nick.
So yeah, just noon, just to be safe.
Okay,
Yeah.
sounds good.
I'm here on
Now,
Zoom or Collaborate, by the way.
Use